I'm so glad you found your way here tonight. Whether you've been lying here for 5 minutes or 2 hours, you're in exactly the right place. Tonight we're going on a very gentle journey together, out beyond the planets, past the stars, and all the way to the very edge of what light itself has ever been able to show us. We're going to explore light years. Not in a complicated, textbook kind of way, but slowly, softly, in a way that lets your mind drift and float wherever it wants to go. Before we begin, if this kind of thing brings you a little peace at night, it would mean the world to us if you hit the like button. And if you haven't already, please do subscribe. It really does help other people out there, people just like you, lying in the dark and needing somewhere calm to rest their thoughts. It helps them find us. So thank you truly for being part of this little community. And one more little thing before we drift off together. We'd love it if you left us a comment letting us know roughly how many hours sleep you normally get each night. Are you a solid 7 or 8? A restless 5? Or are you one of those rare, magical 9-hour sleepers? We're genuinely curious and we read every single one. Tonight's video is called Relaxing Space Light Years Facts to Fall Asleep To. And we're going to take it very, very slowly. So go ahead and get comfortable. Shuffle your pillow, pull your blanket up a little higher if you need to. Let your shoulders drop, let your jaw relax. There's absolutely nowhere you need to be right now and nothing you need to do. You're just here. And the universe is waiting very patiently to tell you a few of its quietest secrets. Let's begin. Into the dark between the stars. So let's start at the very beginning with a question that seems almost too simple. What is a light year? You might have heard the term before, maybe in a film or a documentary or something you half read before bed one evening. And you might have wondered, even just briefly, whether it's a measurement of time. After all, it has the word year in it. It sounds like it should be about time. But a light year is actually a measurement of distance. It's the distance that light travels in a single year. And when we sit with that for a moment, when we really let it settle in, it becomes one of the most beautiful ideas in all of science. Think about light for a second. The light that comes through your window in the morning, the soft glow of a lamp. That thing, that invisible, weightless, almost magical thing, moves faster than anything else in the universe. Nothing has ever been observed traveling faster. Not a spacecraft, not a radio signal, not a thought, nothing. And in a single second, light travels just under 300,000 kilometers. That's roughly the distance you'd cover if you wrapped a tape measure around the Earth 7.5 times in 1 second while you were just lying there. Now hold on to that thought for a moment, because here's where it gets truly wonderful. A light year is how far light travels not in a second, but in an entire year. 365 days. Every second of every hour of every day, light is covering that impossible distance. And at the end of a full year, the total comes to just under 10 trillion kilometers. 10 trillion. That's a 10 followed by 12 zeros. If you wrote it out in full, it would stretch across your bedroom wall, probably several bedroom walls. Astronomers arrived at this number through very precise calculation. They take the exact speed of light, which has been fixed and defined since 1983. and they multiply it by the length of what's called a Julian year, not a calendar year exactly, but a standardized scientific year of 365.25 days, made up of exactly 86,400 seconds each. This gives a precise and consistent answer that scientists anywhere in the world, in any era, can rely on. 1 light year, 9.46 trillion kilometers, 5.88 trillion miles. Now, why do we need a unit this big? Well, imagine you were trying to describe the distance to a nearby star using kilometers. The nearest star to our Sun is called Proxima Centauri. In kilometers, it sits about 40.2 trillion kilometers away from us. That number is almost impossible to hold in your mind. It's too big to feel real. But in light years, Proxima Centauri is 4.24 light years away. That's a number a human brain can actually start to grasp. 4 years of light travel, 4 years of that impossible, tireless 300,000 kilometers per second speed, running without rest. And Proxima Centauri is our nearest neighbor. Most stars are far, far further than that. The light year gives astronomers, and all of us really, a language for talking about space that doesn't immediately collapse under the weight of too many zeros. But here's the thing about the light year that really changes the way you see the sky at night. Because it isn't just a measure of distance, it's also, quietly and almost secretly, a measure of time. When we look at Proxima Centauri, we are not seeing it as it is right now, in this moment, while you lie there with your eyes closed. We are seeing it as it was 4.24 years ago. The light that reaches your eye tonight left that star 4 years ago and has been traveling ever since through the cold and perfect dark until it arrived here. You are not looking at the present sky. You are looking at the past. Every single star you've ever seen on a clear night is a window into a different moment in history. Some of those stars are showing you light from 100 years ago, some from 1,000, some from tens of thousands of years in the past. The night sky is not a single frozen picture. It is a layered, shimmering collection of different moments all arriving at your eyes at once. Astronomers call this look-back time, and it means that every time you look up, you are, in the most literal and physical sense, a time traveler, passively, effortlessly, just by opening your eyes. This idea that light takes time to travel, it sounds obvious now. But for most of human history, people believed light was instantaneous, that when you opened your eyes, you saw the world as it was, right now, with no delay at all. The first person to seriously challenge this was a Danish astronomer named Ole Romer, working in Paris in 1676. He was watching the moons of Jupiter. Specifically, he was observing a moon called Io, which orbits Jupiter and regularly disappears behind it, like a clock ticking. He noticed something strange. The timing of Io's disappearances wasn't consistent. When the Earth was moving away from Jupiter in its orbit, the eclipses seemed to run slightly late. When the Earth was moving closer, they ran slightly early. Romer realized the only explanation was that light had to travel to reach him, and that extra distance was causing the delay. He estimated the speed of light as around 214,000 kilometers per second. That's about 75% of the actual value we know today. For a man using the instruments available in 1676, that is extraordinary. Then, in 1728, an English astronomer named James Bradley refined the estimate further. He was studying something called stellar aberration, the way stars appear to shift very slightly in position depending on where the Earth is in its orbit around the Sun. Think of it like walking in the rain. If you're standing still, the rain falls straight down, but if you run, the rain seems to angle toward your face. Stars do something similar with light as the Earth moves. By measuring this effect carefully, Bradley calculated a speed of light even closer to the modern value. These were quiet, patient, meticulous men, working with telescopes and handwritten calculations, slowly pulling one of the universe's great secrets into the light. And because of their work, and the work of many who followed them, we eventually arrived at the light year, a unit of distance that is also, always, a unit of time. So tonight, as you rest here, as your breathing slows and your thoughts begin to soften and drift, just hold that gently in your mind. The light coming through your window right now, the faint light from the stars you might have seen earlier this evening, that light has been traveling for years, some of it for centuries. It left its source long before you were born, long before your parents were born, perhaps long before anyone alive today was born. And it traveled all that way, across the cold and silent dark, to reach you tonight, right here. There's something very comforting in that if you let yourself feel it. The universe is unimaginably vast and ancient and mostly empty, and yet somehow all that light keeps arriving, quietly, faithfully, right on time. Rest now. We'll continue in just a moment. The sky is a time machine. Let's stay with this idea of look back time for a little while longer, because the more gently we turn it over, the more extraordinary it becomes. We touched on it just now. The idea that when you look at a star, you're seeing the past. But I'd love to take you a little deeper into that tonight in a very slow and unhurried way, because the universe has arranged itself into what you might think of as nested layers of history, each one further back in time than the last, all visible from right where you are, lying in your bed on this small and quiet planet. Let's start close to home. When you look at the moon on a clear night, that soft silver light you see has actually been traveling for 1.3 seconds before it reaches your eyes, just over a second. The moon is not very far away in cosmic terms. It's our closest neighbor in space, and light covers that distance almost instantly. But even so, what you see is not the moon as it is right now. It is the moon as it was a heartbeat ago. The sun is a little further. When you see sunlight, whether it's flooding through your curtains in the morning or painting the sky gold in the evening, that light left the surface of the sun 8.3 minutes before you saw it. The warmth on your skin on a summer afternoon is 8 minutes old by the time it reaches you. If the sun were to simply switch off right now, we wouldn't know for over 8 minutes. We'd sit here in our sunlit afternoon for a little while longer, completely unaware. Jupiter, our solar system's great giant, sits much further out. The light from Jupiter takes around 40 minutes to reach us, depending on where both planets are in their orbits. So when astronomers like Romer were watching Io disappear behind Jupiter, they were watching something that had already happened 40 minutes earlier. They were studying the past without even fully realizing it. Now let's step outside our solar system entirely. Proxima Centauri, our nearest stellar neighbor, is 4.24 light years away. We talked about this already, but I want you to really feel the scale of that. The light reaching us from Proxima Centauri tonight set off in the autumn of 2021 approximately, before many things that have happened in your life since then had yet occurred. That star has been silently sending its light toward you this whole time, patient and unwavering, and it's only just arriving now. Now let's go further. The center of our own galaxy, the Milky Way, lies somewhere between 26 and 27,000 light years from Earth. When we look toward the galactic center, we are seeing it not as it is in the year we're living in, but as it was 26,000 years ago. At that point in history, our ancestors were living through the last ice age. Woolly mammoths still roamed the earth. Modern human civilization as we know it, our cities, our languages, our written history, none of it existed yet. And yet the light that shows us the heart of our own galaxy began its journey in that ancient world. And we haven't even left our own galaxy yet. Let's go one step further. Our nearest large galactic neighbor is the Andromeda Galaxy. You might have seen it on a very clear, dark night. It appears as a faint smudge of light barely visible to the naked eye. What you are seeing when you look at Andromeda is light that has been traveling for 2.5 million years. 2.5 million years ago, the earliest members of our genus, the very first humans in any meaningful sense, were just beginning to walk upright on the plains of Africa. Our entire history as a species, every civilization, every invention, every story ever told, every song ever sung, all of it fits inside the time it has taken that light to reach you. And it arrives tonight, so softly, so quietly, as a tiny smudge in a dark sky. This is what the night sky really is. Not a ceiling, not a backdrop, but a vast and layered archive of history written in light. Every object in the sky is showing you a different chapter. The moon shows you a second ago. The sun shows you 8 minutes ago. Proxima Centauri shows you 4 years ago. The galactic center shows you 26,000 years ago. Andromeda shows you 2.5 million years ago. And if you had a powerful enough telescope, you could keep going. You could look at galaxies hundreds of millions of light years away, and you would be seeing them as they existed hundreds of millions of years ago, before the dinosaurs, before complex life, before almost anything we would recognize on this planet. The furthest things we've ever observed with our most powerful telescopes show us light that has been traveling for over 13 billion years. We are looking almost all the way back to the beginning of everything. There is something that feels, to me at least, deeply peaceful about this. The universe doesn't hide its history. It carries it, written in light, and delivers it to whoever is patient enough to look up. Now, there is something even stranger tucked inside all of this, and I want to share it with you gently because it's one of those ideas that can feel a little unsettling at first, but then if you hold it just right, it becomes rather beautiful. Some of the things we see in the sky may no longer exist. The light we receive is a message from the past, but the object that sent it has had all this time to change or to disappear entirely. There are stars visible to the naked eye tonight that may already be dead. They may have exploded, collapsed, burned out long ago, but their light is still reaching us. They still appear to shine because their last light is still traveling toward us across all that distance. We can never see the universe as it actually is right now, only as it was, and this gives us a very particular kind of humility. All our observations, all our photographs, all our maps of the cosmos, they are historical documents. Beautiful, astonishing, precise historical documents, but documents of the past nonetheless. There is actually one extraordinary example of this that I'd love to share with you now. In the constellation of Serpens, there is a structure photographed by the Hubble Space Telescope and later the James Webb Space Telescope that became one of the most iconic images in the history of astronomy. Tall, dark, dramatic columns of gas and dust, lit from within by the light of young stars being born inside them. They are called the Pillars of Creation. They sit about 6,500 to 7,000 light years away from Earth, and they are genuinely breathtaking to look at. But here's the quiet and slightly eerie detail. There is evidence gathered from the Spitzer Space Telescope that the Pillars of Creation may have already been destroyed. A nearby supernova, a star that exploded, appears to have sent a shock wave through that region of space roughly 6,000 years ago. A shock wave powerful enough to have obliterated those magnificent columns entirely. But because they are 7,000 light years away, the light showing us that destruction has not yet reached us. We are still seeing the pillars standing tall, still lit, still beautiful, still intact. What we're looking at may already be gone. The light carrying the news of their destruction is on its way. Astronomers estimate it won't arrive for another 500 to 1,000 years. Somewhere between 500 and 1,000 years from now, our descendants will look toward the Eagle Nebula and see something different. The pillars will be gone from the sky, but tonight they are still there, still glowing, a ghost of something that may no longer exist, preserved perfectly in light, still traveling faithfully across the dark to reach us. And I find that strangely moving. That light carries on. Even after its source is gone, it just keeps traveling, quiet and purposeful and utterly unaware of what it's left behind. Much like the thoughts we carry from the past. Long after certain moments are over, the light of them is still reaching us, still arriving, still visible if we choose to look. So as your eyes grow heavy now, as the room around you grows quieter and your breathing finds its own gentle rhythm, I want to leave you with this. You are not separate from the universe. You are inside it, part of it. And every photon of light that has ever reached your eyes has been traveling, sometimes for millions of years, to find you specifically. Right here, right now. The night sky isn't just beautiful, it's addressed to you. Rest now. Let that thought carry you a little further towards sleep. We have more to explore together, but there's no hurry. The stars have been waiting for billions of years. They'll wait a little longer. If you're finding it hard to drift off tonight, even with all these stars to keep you company, you might want to take a peek at the description below this video. I often pop in little recommendations down there. Things that have genuinely helped people get a better night's rest. No pressure at all, just a quiet little resource if you need it. Now let's get back to the stars, where the light comes from. We've been floating gently through the idea of how far light travels and how that distance becomes a kind of time. But I'd love to slow down now and tell you about some of the remarkable people who helped us understand all of this. Because behind every beautiful idea in science, there are human beings, patient, curious, sometimes frustrated human beings who spent their lives peering through lenses and scribbling calculations in candlelit rooms, trying to understand something vast and quiet and almost impossibly elusive. Let's go back to the 19th century for a little while. By the early 1800s, scientists had a reasonable estimate of how fast light traveled, but no one had yet managed to measure the distance to any star beyond our own sun. We knew the stars were out there. We could see them. We'd been watching them for thousands of years, but how far away they actually were remained completely unknown. It was one of the great unanswered questions in all of science. The challenge was a technique called parallax, and it's actually a very human, very intuitive idea. Hold your finger up in front of your face. Now close your left eye and look at it with your right. Then switch. Open your left eye and close your right. Notice how your finger seems to jump slightly against the background, even though it hasn't moved. That's parallax. The slight shift in apparent position caused by looking at something from two slightly different angles. Now, imagine doing that with a star. If you observe a nearby star in January, and then observe it again in July, when the Earth has moved to the opposite side of its orbit around the Sun, the nearby star should appear to shift very slightly against the backdrop of much more distant stars behind it. The closer the star, the bigger the shift. The problem is that even for the nearest stars, this shift is incredibly, almost maddeningly tiny. We're talking about fractions of an arcsecond. An arcsecond is 1/3600th of a degree. The kind of precision that pushed the instruments of the early 19th century almost to their absolute limits. Several astronomers raced to be the first to measure it successfully, and the winner, announced in 1838, was a man named Friedrich Wilhelm Bessel. Bessel was the director of the Königsberg Observatory in what is now northern Poland. He was meticulous, methodical, and enormously skilled. He chose his target carefully, a star called 61 Cygni in the constellation of the Swan. He chose it because it appeared to move slightly across the sky over time, what astronomers call a high proper motion, and this suggested it was relatively close to us, close enough that its parallax might be measurable. He was right. After months of careful, painstaking observation, Bessel announced that 61 Cygni was approximately 660,000 astronomical units away, which sounds enormous and is. But Bessel also noted something quietly remarkable. He pointed out that it would take light approximately 10.3 years to cross that distance. He was using the idea, even if he hadn't yet named it. He was thinking in light years before the term even existed. And the actual distance to 61 Cygni? We now know it to be about 11.4 light years. Bessel's measurement, made with instruments you could hold in your hands, in an observatory on a cold Prussian hilltop in 1838, was remarkably close. The term light year itself came a little later. In 1851, a German science writer named Otto Uhle published an article called Beautifully, What We Read in the Stars. And in that article, he introduced the word Lichtjahr, light year. He compared it to something called a walking hour, the distance a traveler covers in an hour of walking on foot. A way of measuring distance through movement over time. He was making the vastness of space feel human, relatable, something a person could almost hold in their mind. It took a little while for the term to catch on. Some professional astronomers preferred a unit called the parsec, which we'll come to in a moment. But for the general public, for anyone trying to understand the scale of the universe, the light year was irresistible. It answered two questions at once. How far away is that star? And how long ago did its light leave? In one word. One beautiful, elegant, slightly paradoxical word. Now let's talk about the parsec, because it appears in a lot of astronomical writing, and it's worth understanding what it actually is. A parsec is equal to about 3.26 light years, and it comes directly from the parallax technique we just talked about. If a star is 1 parsec away, it will show a parallax shift of exactly 1 arcsecond when observed from opposite sides of the Earth's orbit. The name itself is a contraction of parallax and arcsecond. Parsec. It was coined in 1913 by a British astronomer named Herbert Hall Turner, and it became the unit of choice for professional research precisely because it's tied directly to the observational method used to measure stellar distances. When you're deep in the mathematics of galactic structure, parsecs are very convenient. Astronomers use kiloparsecs for distances within the galaxy, megaparsecs for distances between galaxies, and gigaparsecs for the very largest scales of the universe. But for the rest of us, lying here in the dark, the light year remains the more poetic and intuitive choice, and there's nothing wrong with that. Now, alongside the light year and the parsec, there's a third unit worth knowing about, one used much closer to home, the astronomical unit, or AU. 1 astronomical unit is the average distance between the Earth and the Sun, about 149 million kilometers. It was formally standardized in 2012 as an exact fixed value, and it's the unit astronomers use for distances within our solar system. The distance from the Sun to Jupiter, for example, is about 5.2 astronomical units. Saturn sits at about 9.5. Neptune, the furthest of the 8 planets, orbits at about 30 astronomical units. Even the Voyager spacecraft, launched in 1977 and now the most distant human-made object in history, is only a few hundred astronomical units away, barely a whisper of a light year. These 3 units together form what astronomers call the cosmic distance ladder. Each rung of the ladder covers a different range of scales, astronomical units for the solar system, light years or parsecs for nearby stars and our galaxy, megaparsecs and beyond for the vast distances between galaxies and galaxy clusters. And climbing that ladder has been one of the great achievements of human science. Each rung depends on the ones below it. To measure the distance to a nearby star, you need to know the size of the Earth's orbit in astronomical units. To measure the distance to a faraway galaxy, you need to know the distance to nearby stars as a reference. Everything connects. Everything builds on everything else. It's a little like the way trust works in a way. You build it carefully, step by step, each piece of understanding resting on everything that came before. Now, there's one more thing I'd like to leave you with before we move gently on. Something I find quietly astonishing about the way our unit of measurement was created. The speed of light, that number we've been talking about, around 299,792 kilometers per second, wasn't always known precisely. It was measured and refined over centuries. Romer in 1676, Bradley in 1728. Then a French physicist named Armand Fizeau in 1849, who did something wonderfully inventive. Fizeau set up a beam of light, aimed it at a mirror 8 kilometers away, and placed a rapidly spinning toothed wheel in the path of the light. As the wheel spun faster and faster, there came a speed at which the returning light, bouncing back from the distant mirror, was blocked by the next tooth in the wheel. By measuring the rotation speed of the wheel at that precise moment, he could calculate how long the light had taken to travel the 16-kilometer round trip. He got a value of about 315,000 kilometers per second. Not perfect, but extraordinary for an experiment conducted entirely on Earth with a spinning wheel, a candle, and a mirror 8 kilometers away. A few years later, Leon Foucault refined the technique using rotating mirrors and discovered something equally remarkable along the way. He proved that light travels more slowly through water than through air. This was significant because it helped settle a long-running debate about whether light behaved as a wave or as a stream of particles. Waves slow down in denser mediums. Particles, on some theories, should speed up. Foucault's result was a quiet but decisive blow for the wave theory. And then, in 1983, something definitive happened. Scientists no longer needed to measure the speed of light at all. The speed of light was fixed, defined, made exact by international agreement. The meter itself was redefined as the distance light travels in a vacuum in exactly 1,299,792,458th of a second. The universe had been doing the measuring all along. We just finally agreed to let it. And so the light year, which began as a human attempt to describe something almost too large to comprehend, turns out to be built on a constant that is woven into the very fabric of reality. The speed of light isn't just fast, it's fundamental. It's part of the structure of space and time itself. That's worth holding gently as you begin to drift. All those centuries of careful people watching moons and spinning wheels and distant mirrors, slowly climbing toward a truth that was always there, patient and constant and exact, just waiting to be found. Let your breath slow a little now. Let the images fade. The observatory on the Prussian hilltop, the spinning wheel in the candlelight, the mirror 8 kilometers away in the dark, all of them reaching in their own quiet way toward the same light. We'll continue shortly. The most distant light. We've come a long way together tonight already, from the basics of what a light year is, through the layered history written in the night sky, through the patient scientists who measured it all so carefully. Now I'd like to take you somewhere even further, to the very edge of what we've ever been able to see. Because the story of light years doesn't end with nearby stars or even with our own galaxy. It keeps going, further and further back in time, further and further out into space, until we reach objects so distant that the light reaching us tonight began its journey before our planet even existed. Let's start with a star. In 2022, astronomers using the Hubble Space Telescope made a discovery that genuinely stopped people in their tracks. They detected the light from a single individual star, not a galaxy, not a cluster, but one solitary star, further away than any individual star had ever been observed before. They gave it a nickname, Arundel, a beautiful Old English word meaning morning star or rising light. Arundel's official designation is a little less poetic, WHL 0137-LS, but the nickname suits it perfectly because this star is a kind of ancient dawn light reaching us from the very early universe. The light we've detected from Arundel has been traveling for 12.9 billion years. Let that settle for a moment. 12.9 billion years. Our solar system, our sun, our Earth, none of it existed when that light began its journey. The universe itself was less than 1 billion years old. Now you might wonder, how on earth did we see something so impossibly far away and so impossibly faint? A single star at that distance should be completely invisible to us, even with the most powerful telescopes ever built. The answer is something called gravitational lensing, and it is one of the most extraordinary phenomena in all of astronomy. When light passes close to a very massive object, a large galaxy or a galaxy cluster, the gravity of that object bends the light, curves it, like a lens made not of glass but of pure gravity. This bending can sometimes cause a distant object to appear much brighter than it otherwise would, because the gravitational lens focuses and amplifies its light toward us. In the case of Arundel, a massive galaxy cluster called WHL 0137-08 happened to sit almost perfectly between us and the star. and it acted as a cosmic magnifying glass, amplifying Arendel's light by a factor of at least 4,000. Without that lucky alignment, we would never have seen it at all. 4,000 times brighter than it would otherwise appear. And we still needed the Hubble Space Telescope, and later the James Webb Space Telescope, to detect it. When the James Webb Telescope examined Arendelle more closely, it was able to gather enough light to do something called spectroscopic analysis. Essentially, it spread the light out into its component colors like a prism and read the chemical fingerprint hidden within. What it found was that Arendelle is what astronomers classify as a B-type star, massive, intensely hot, burning at temperatures around twice that of our own sun, and millions of times more luminous. And here is the haunting detail. Stars like Arendelle don't live long. They burn so brightly and so fiercely that they exhaust their fuel in only a few million years. Our sun, a much more modest star, will last around 10 billion years in total. But a star like Arendelle, vast and brilliant and burning with that intensity, survives for only a few million years at most. Arendelle's light has been traveling toward us for 12.9 billion years. But the star itself almost certainly burned out within a few million years of forming, which means Arendelle has been dead for more than 12 billion years. What we detected was not a living star. It was a memory, a ghost of light, still traveling faithfully across the universe long after its source had vanished entirely. We are seeing, with our telescopes and our mathematics and our careful measurements, something that no longer exists, something that died before our sun was born, before our planet formed, before the first microbes stirred in the first ancient ocean. There is something both lonely and magnificent about that. Now let's go even further. Let's leave individual stars behind entirely and look at the earliest galaxies. In recent years, the James Webb Space Telescope has been doing something remarkable. It has been looking further back in time than any telescope before it, finding galaxies that formed in the very earliest chapters of the universe's history. In 2024, astronomers confirmed the discovery of a galaxy with the designation JADES-GS-Z14-0, and its numbers are almost incomprehensible. This galaxy has what scientists call a redshift of 14.32. Redshift is a measure of how much the light from an object has been stretched by the expansion of the universe during its journey to us. The higher the redshift, the further away the object and the further back in time we're looking. A redshift of 14.32 places this galaxy just 290 million years after the Big Bang. The universe is approximately 13.8 billion years old. 290 million years after the Big Bang means we are looking at a time when the universe was barely 2% of its current age. The cosmos was still in what astronomers beautifully call the cosmic dawn. The very first stars and galaxies were just beginning to ignite for the first time, lighting up a universe that had, until that point, been dark. And yet, JADES-GS-Z14-0 is already surprisingly large, already surprisingly luminous, already 1,600 light years across. And when astronomers examined it with a ground-based telescope array called ALMA in early 2025, they found something that genuinely surprised them. They found oxygen, not as a curiosity, not a trace, actual ionized oxygen present in significant quantities in a galaxy that existed less than 300 million years after the universe began. Why does that matter? Because oxygen isn't a primordial element. It wasn't created in the Big Bang. Oxygen is made inside stars through nuclear fusion and then scattered into space when those stars die in enormous explosions called supernovae. For oxygen to be present in a galaxy at this epoch, multiple generations of massive stars must have already lived out their entire lives and died, enriching the surrounding gas with heavy elements. Multiple generations, in less than 300 million years. Our models of how galaxies form and evolve had not predicted this. They didn't account for things happening this quickly. JADES-GS-Z14-0 is, in the gentlest possible terms, a problem for our theories. A beautiful, astonishing problem that is currently keeping a great many cosmologists very busy. The universe, it turns out, got to work much faster than we thought. Now here is something I'd like you to sit with for a moment, because it involves a subtlety about light years that we haven't quite touched on yet. And it's one of those ideas that initially seems confusing, but resolves itself into something almost meditative. When we say JADES-GS-Z14-0 is 13.5 billion light years away, that's the light travel distance, the time the light has spent traveling. But because the universe has been expanding the entire time that light was in transit, the actual current distance to that galaxy is much greater. The galaxy isn't where the light came from, it's moved on. Space itself has stretched and expanded, carrying that galaxy further and further away from us every second, even as its ancient light was making the journey toward us. The current estimated distance to JADES GS Z14-0, accounting for all that expansion, is around 33.8 billion light years. The universe is 13.8 billion years old, yet objects within it can be 33 billion light years away from us. This seems impossible. How can something be further away than light could have traveled in the entire age of the universe? The answer is that space itself expands. The distance between objects grows, not because they are moving through space, but because space is stretching. It has been doing so since the very beginning, and in the early universe, it was stretching extraordinarily fast. This is what makes cosmology so endlessly surprising. Our everyday intuitions about space and time and distance simply don't apply at these scales. The universe plays by rules that feel almost dreamlike when you first encounter them. Objects further away than light could ever reach us from, galaxies receding faster than the speed of light, not by moving through space, but by being carried on the expansion of space itself. Light that has been traveling for billions of years, only to reveal something that no longer exists in the form we see. And yet, through it all, the light comes, patient and constant and precise, carrying its ancient message across an expanding, curving, almost incomprehensible cosmos to arrive here tonight at the mirrors of our telescopes. There is so much we are still learning, so much that surprises us, but the surprises are always beautiful ones. Each new discovery doesn't make the universe feel less wonderful. It makes it feel more so. And perhaps that's a good thing to carry into sleep, that the universe is larger and stranger and more generous with its mysteries than we ever expected. That there is always more to discover, always another light on its way toward us, carrying news from somewhere ancient and extraordinary. You don't need to understand it all tonight. Nobody does. Not even the cosmologist lying awake thinking about JADS-GS-Z14-0 fully understand it yet. But you can feel it, the scale of it, the age of it, the quiet faithfulness of light traveling all that way just to be seen. Let your thoughts go soft now. Let them drift out toward those ancient galaxies if they want to, or let them simply dissolve into the dark. Either way, you're doing beautifully. Rest here for a moment. We'll continue when you're ready. The universe is humming. We've traveled a very long way tonight, past nearby stars, through ancient galaxies, all the way to the edge of what light has ever been able to show us. And I'd like to take you somewhere a little different now, somewhere that feels in a strange and lovely way, a little closer to home. I'd like to tell you about sound, not the sound of the universe as it is tonight. Not the quiet hum of distant galaxies or the crackle of distant stars, but the sound of the universe as it was in its very earliest moments. A sound so ancient and so vast that it makes everything else we've talked about tonight feel almost recent. Because the early universe was not silent. It was, in fact, extraordinarily loud. In the first few 100,000 years after the Big Bang, the universe was a very different place from the one we inhabit now. It was unimaginably hot and dense, so hot that matter and light were locked together in a kind of glowing, churning plasma. Protons and electrons couldn't yet combine to form neutral atoms. They were all flying around separately, colliding constantly in a state of perpetual energetic chaos. And within that chaos, something was happening that cosmologists find endlessly fascinating. There were waves, pressure waves, moving through the plasma of the early universe in exactly the same way that sound waves move through air. Two competing forces were in constant tension: gravity, which pulled matter together into denser regions, and the pressure of all that radiation, light pressure essentially, which pushed back outward again. Matter would compress, radiation would push it back out, it would expand, compress again, and so on, rippling outward in great spherical waves through the primordial plasma. These are called baryon acoustic oscillations. It's a technical name for something that is, at its heart, quite simple. The universe, in its infancy, was ringing like a bell. Now, how low was the pitch of this cosmic ringing? Imagine the lowest note you've ever heard. The deepest, most resonant bass note from a cathedral organ. or the subsonic rumble you feel in your chest at a live concert. Now go lower, much lower. Keep going far beyond anything a human ear could ever detect. The frequency of these primordial sound waves was somewhere around 10 to the power of minus 12 hertz. That means one complete wave cycle took between 20,000 and 200,000 years to complete. One single wave, one compression and expansion, 20,000 years. On a musical scale, this sits approximately 48 to 52 octaves below concert A. For reference, the lowest note on a standard piano is about 4 octaves below concert A. We are talking about something 48 octaves below that. A note so impossibly deep that our entire experience of music and sound doesn't even begin to approach it. And yet it was real, it was physical, it was happening, and it was extraordinarily loud. Scientists have been able to estimate the volume of these primordial sound waves by studying tiny variations in the temperature of something called the cosmic microwave background. We'll come to that in a moment. But the pressure variations in those early waves correspond to a sound level of approximately 110 decibels. 110 decibels is roughly the volume of a rock concert heard from the front row, or a jet engine at close range, or standing next to a pneumatic drill on a busy street. The early universe was as loud as a rock concert, everywhere, all at once, for hundreds of thousands of years. I find that image genuinely delightful. This vast, ancient, unimaginably hot cosmos, ringing and roaring and vibrating with acoustic waves that stretched for hundreds of thousands of light years, before a single star had yet formed, before a single planet existed, before anything we would recognize as matter had yet settled into the forms it wears today. And then, quite suddenly, in cosmic terms, it stopped. About 380,000 years after the Big Bang, the universe had expanded and cooled enough that something remarkable happened. Electrons and protons were finally able to combine to form neutral hydrogen atoms. This moment is called recombination, and it changed everything. Before recombination, the plasma was opaque. Light couldn't travel freely through it. It was constantly being scattered and absorbed and re-emitted. The universe was a thick, glowing fog. But when neutral atoms formed, the fog cleared. Light was suddenly free to travel, and it did, in all directions, filling the universe. That light is still traveling today. It's been traveling for 13.8 billion years, cooling and stretching as the universe expanded, until today it exists as a faint, cold glow of microwave radiation that permeates all of space equally. In every direction you look, if you had the right instruments, you would detect it. Always there, always the same, the oldest light in the universe. It's called the cosmic microwave background, and its temperature today is just 2.7255 degrees above absolute zero, the coldest possible temperature. The universe has been cooling for 13.8 billion years, and this is what that ancient light has become. The cosmic microwave background is, in the most literal sense, a photograph of the early universe. a snapshot taken 380,000 years after the Big Bang, still reaching us today, still telling us things. And what it tells us is extraordinary, because it isn't perfectly uniform. It has tiny variations, fluctuations in temperature of about 1 part in 100,000. These tiny ripples are the fingerprints of those ancient sound waves we were just talking about. The acoustic oscillations froze into the distribution of matter at the moment of recombination, like a wave pattern frozen into the surface of a cooling liquid. Those frozen ripples became the seeds of everything that followed. Over billions of years, gravity amplified those tiny variations. Dense regions attracted more matter. Sparse regions grew emptier. Those ancient frozen sound waves became the scaffolding of the universe, the template on which all the galaxies, all the galaxy clusters, all the vast cosmic web of structure we observe today was eventually built. Everything you can see in the night sky, every star, every galaxy, every cluster, owes its position and existence to those ancient, impossibly low, rock concert loud pressure waves that rang through the universe in its first few 100,000 years. The universe didn't just begin with a bang, it began with a song. Now those frozen ripples left a very specific imprint. Because the sound waves could only travel so far before recombination froze them in place, there is a characteristic scale in the distribution of matter throughout the universe. A preferred distance between galaxy clusters, like the spacing between the peaks of a wave. This is called the sound horizon. At the time of recombination, the sound horizon was about 450,000 light years across. But because the universe has been expanding ever since, that scale has stretched. Today, it corresponds to a distance of roughly 490 million light years. This gives astronomers an extraordinary tool. Because we know precisely what that scale should be, we can use it as a ruler, a standard ruler of known length that we can use to measure distances across the universe. By observing how galaxy clusters are distributed at different distances and comparing that to the expected sound horizon scale, we can measure the expansion history of the universe itself. Recent results from a survey called the Dark Energy Spectroscopic Instrument, or DESI, have measured this scale to a precision of less than 1%. Less than 1%, using the fossilized echoes of sound waves that rang through the universe nearly 14 billion years ago. It's one of the most beautiful examples I know of science turning something seemingly impossibly ancient and abstract into a precise and practical measurement. The universe left us a ruler, hidden in the distribution of galaxies, written in the language of sound, and we found it. Now there is one more thing I'd like to gently share before we let this chapter rest. We said the cosmic microwave background is the oldest light in the universe, the furthest back we can see. But it isn't quite the beginning. There was something before it. Before recombination, before the universe became transparent, light couldn't travel freely. So we can't see further back than that moment, 380,000 years after the Big Bang, using light at all. The universe before that point is hidden from us behind a luminous veil. But there are other messengers. Neutrinos, tiny, nearly massless particles, decoupled from the rest of matter even earlier than light did, about 1 second after the Big Bang. In principle, a neutrino telescope sensitive enough could detect a cosmic neutrino background that predates even the CMB. We haven't managed it yet. The technology doesn't quite exist. But the neutrinos are out there, filling the universe, carrying information from the very first second of existence. And then there are gravitational waves, ripples in the fabric of space-time itself, produced by the most violent events in the cosmos. Gravitational waves don't interact with matter the way light does. They pass through everything. They could, in principle, carry information from even earlier than the neutrino background, from the very first fractions of a second after the Big Bang, when the universe was so dense and so hot that our physics begins to break down and our understanding becomes uncertain and humbling. We are listening for those waves now. Experiments like LIGO and its successors are designed to detect them. And in the coming decades, as our instruments become more sensitive, we may begin to hear the universe's very earliest moments, not in light, not in neutrinos, but in the gentle stretching and compressing of space itself. The universe has been speaking since the very first moment, in sound waves, in light waves, in gravitational waves, in every frequency imaginable and many we can barely imagine. We are still learning to listen, and maybe that's a perfect thought to carry with you now as your body grows heavier and your mind grows quieter. That the universe has been singing since before the first star, before the first galaxy, before the first atom even formed. A song in frequencies far too low and far too ancient for human ears. But we found it anyway. We looked at the arrangement of galaxies across billions of light years of space and heard, in the pattern of their distribution, the echo of a sound that rang out nearly 14 billion years ago. Isn't that something? Let your breathing slow a little more now. Let your thoughts drift where they want to. Maybe out toward those ancient sound waves rippling through the hot young universe. Maybe toward the soft, cold glow of the microwave background, wrapping the entire cosmos like the gentlest imaginable blanket. Or maybe just into the quiet of your own room, your own breath, your own particular darkness, all of it connected, all of it part of the same story. You're doing so well. Rest now gently. We have just a little more to share before we hand you over to the music and let you float the rest of the way to sleep. And so we've come very gently to the end of our journey together tonight. We started with something simple, a question about what a light year actually is. And from there we traveled further than most people ever think to go before bed, through the layered history written in the night sky, through the patient scientists who spent their lives measuring something almost too fast and too vast to measure, through the most distant light ever detected, ancient starlight that began its journey before our planet existed, and finally through the sound of the very early universe itself, a primordial song frozen into the fabric of everything around us, and all of it connected by one simple, beautiful idea. That light takes time to travel. That distance and time are, out there in the universe, the same thing wearing different clothes. Every photon that has ever reached your eyes has been on a journey. Some for seconds, some for years, some for billions of years. All of them arriving quietly, faithfully, without fanfare at exactly the right moment. Rather like sleep when it finally comes. You don't need to hold on to any of this tonight. You don't need to remember the names or the numbers or the distances. Just let it all dissolve into the dark behind your eyes, the way starlight dissolves into the sky at dawn, gently, gradually, without effort. Your body knows how to rest. It has always known. Sometimes it just needs a little company on the way there. Thank you so much for spending this time with us here on Orbit into Sleep. It genuinely means a lot that you chose to be here tonight, in this quiet corner of the universe, listening. If this helped you rest a little easier, please do leave us a like before you drift off, and subscribe if you haven't already. It helps other restless minds find their way here, and that feels like a genuinely lovely thing to be part of. Now the music is coming, and it's going to carry you the rest of the way. You don't need to do anything at all. You don't need to think or wonder or understand. Just let the sound fill the room and let your mind do whatever it would like to do. Wander if it wants to wander. Dream if it wants to dream. Float if it wants to float. The universe is 13.8 billion years old, and it has been quietly, patiently expanding every single second of that time. There is no hurry. There never was. Good night. Sleep beautifully.